Imagine looking up at the night sky. You see stars, planets, and vast dark emptiness. For centuries we thought this emptiness was just that, empty. But what if I told you that this vacuum, this space between everything, is not empty at all? What if it's fizzing with energy, a hidden force that is pushing the entire universe apart? This is one of the most profound and baffling ideas in all of modern science. It's a concept that started with a simple number in an equation, but has grown into the biggest mystery we face in our quest to understand the cosmos. This mysterious energy of space itself is what physicists call the cosmological constant. The idea is both simple and, honestly, mind-boggling. Think of it as a kind of anti-gravity. This strange energy was first imagined over a century ago by Albert Einstein. He didn't introduce it to explain an accelerating universe. He didn't even know the universe was expanding. He put it into his equations for a very different reason, one that he would later come to regret. But science has a funny way of bringing old ideas back in new and unexpected ways. In the early 20th century, Albert Einstein had just completed his masterpiece, the general theory of relativity. This was a revolutionary new way of understanding gravity. He proposed that space and time are not separate entities, but are woven together into a single fabric, space-time. Massive objects like stars and planets warp this fabric, and this curvature is what we feel as gravity. The turning point came in 1929, thanks to the work of American astronomer Edwin Hubble. Stationed at the Mount Wilson Observatory in California, Hubble was using the most powerful telescope of his time to measure the distances to faraway galaxies. But what they found was one of the most shocking discoveries in a century of cosmology. When they analyzed their data, they saw that the distant supernovae were fainter than they should have been. The universe was not just expanding, it was accelerating. Something was pushing on the accelerator, overwhelming the force of gravity. Suddenly, Einstein's biggest blunder didn't look like a blunder anymore. It looked like a prophecy. Our best and most fundamental theory of the subatomic world is quantum field theory. According to this theory, the vacuum of empty space is not truly empty. It is a seething, bubbling cauldron of virtual particles that constantly pop in and out of existence. The problem is that when physicists sit down and try to calculate how much of this vacuum energy there should be, the number they get is catastrophically, unimaginably large. The difference between the theoretical prediction and the observed value is a factor of 1 followed by 120 zeros. There is no other disagreement in the history of science that is this large. This glaring discrepancy is what scientists call the cosmological constant problem, or more dramatically, the vacuum catastrophe. To truly appreciate the strangeness of the cosmological constant problem, we need to move beyond the numbers and reach for analogies. So imagine the entire universe is a vast, calm ocean. The galaxies are like tiny boats scattered across its surface. It's as if there is a very gentle, almost imperceptible current flowing through the entire ocean. This current is not like a river. It does not flow in one direction. Instead, it pushes outward everywhere, adding a little bit of space between all the boats, all the time. Imagine a colossal cosmic lottery machine. This machine is designed to spit out universes, and one of its main settings is a dial that controls the value of the cosmological constant. The habitable range on our 120-meter dial is not a meter wide, or even a centimeter. It is a sliver of space so narrow that it is smaller than the width of a single atom. We find ourselves at a remarkable, if humbling moment in the history of science. The cosmological constant problem is the great chasm that lies between what we see and what our best theories predict. Solving this puzzle is not just an academic exercise, it is the single biggest hurdle standing in the way of a truly unified theory of physics. Understanding the cosmological constant is therefore key to understanding our ultimate fate. Is dark energy truly a constant, or could it change over time? Like the unexplained orbit of Mercury that once pointed the way toward general relativity, this glaring discrepancy is our most important clue. It is a signpost, pointing us toward a new and more complete understanding of the universe. The cosmological constant is a testament to the enduring power of the scientific method, to observe, to question, and to accept the universe as it is, not as we wish it to be. The universe is not a closed book. Its most exciting chapters may be yet to be written. waiting for the next generation of explorers to dare to read them.